In Chapter 3 in Pre-Calc 1, where we are, is we're doing polynomials. So we started out with quadratics. So with quadratics, they have the form ax squared plus bx plus c, and that's what my function looks like. Now, if I set this thing equal to 0, then I can find where, if it does cross the x-axis. And when I set it equal to 0, if it factors, I factor it. If it doesn't factor, I throw it in the quadratic equation. And if the discriminant, which is the value underneath the square root, so this is the discriminant, so we can determine the types and how many solutions we have based on that discriminant. Now, if that discriminant is greater than 0, then I'm guaranteed to have two real solutions. They may not be nice numbers, but I'm guaranteed to have two real solutions. If that discriminant is equal to 0, then I'm guaranteed to have one real solution that is a repeating solution. So I actually do get two solutions. It has a multiplicity of 2. So then the last case is when my discriminant is less than 0, and that's when I have two solutions, but they're complex solutions. So if I take a look at something that looks like this, this is a case in which I have two solutions. Those numbers may be nice integer numbers, they may not be nice integer numbers, but I have two solutions. So I may have square roots in the answer, but the square roots of real numbers. So if I have it equal to 0, then it may look something like this, where it is it's just touching and bouncing, and we have a multiplicity of 2. I still have two solutions, but they are repeating solutions. They're not unique. And then the last one, so that's what that one looks like. And then the last one is here, is when I have a quadratic that may look like that, in which I have no solutions because it's not crossing the x-axis. So those are the cases in which you have discriminants that are equal to 0, less than 0, or greater than 0. So those are your three choices. Now, for calculus students, they love doing quadratics, finding the maximum or minima, because they can do a derivative. And they're like, oh, thankfully we get to do that. You all don't get to do derivatives, even if you know how to do it, because I don't teach it to you until calculus. So what you will have to do to find the vertex, to find the minimum, to find the maximum, is you have to do the vertex by using either A, you can complete the square, which, as an example, if I had x squared minus 2x plus 5, and I want to know where that vertex is, then I can do it by completing the square. So I'm basically giving you what we did in like 2 weeks' time in 10 minutes. And this is why you're all like, please don't ever do that again. So I do it by completing the square, and the way I do that is I do x squared minus 2x plus something plus 5 minus that something. The way I figure out what goes there is I take this negative 2 divided by 2, I square it. I put it here, and I put it here. That means these first three terms turn into x minus 1, the quantity squared, and then plus 4. So that's what my function becomes. You can totally do it by completing the square. Do I want to do it by completing the square? Not if I can avoid it. If I do it by completing the square, then I know that my vertex is at 1, 4. That tells me I'm not going to have any real solutions because my vertex is above the x-axis, and my leading coefficient is positive, so I'm not going to have any real solutions. But I do know where my turning point is. It is at 1, 4. That's my turning point. The other way of finding your vertex is finding h, which is negative b over 2a. Once you find h, that is what this value is. This is h, this is k. So I go back to my original function here, and it is x squared minus 2x plus 5. So that is going to give me negative 2 over 2 times a, which is 1. So I still get 1 out for my h. Now I didn't have to do it by completing the square. To find my k value, I need to put that h value into my original function, so f of h, which is f of 1, I put 1 into my original function and I get 1 squared minus 2 times 1 plus 5, which is going to give me 4, which is what I got right here. So I can do my vertex without ever actually finding the value by completing the square. And that's what, well, I would recommend you be fluent in both, because in Pre-Calc 2, where's my Pre-Calc 2 student? In Pre-Calc 2, we're going to be going to conics. So we're going to be looking at circles, and we're going to be looking at parabolas and hyperbolas, and we've got to be fluent in completing the square with x's and y. So I'd recommend you be fluent in both. Oh, yes, and all of those. So that is what we did in 2.3. Now what we did in 2.4 is we took our polynomials and we said if f of x is greater than or equal to 0. What does that mean? It means that we are looking for the x values that produce a y value above the x-axis. So I want to know, where are we above the x-axis? And so we started getting these, which is, say I had f of x is equal to x minus 1, x plus 2, and x minus 3. So we started talking about in chapter 3 and with 2.4 is finding where these polynomials are going to be above the x-axis. Now you can totally do this polynomial without graphing it by doing a sign chart. We're going to do both of them. So if I want to do it by graphing without doing a sign chart, then I've got to determine what the degree of my polynomial is, and we call that degree n. So when you see n, there's asking you what that is saying, I have a degree of polynomial, whatever that is. Without multiplying all of this through, which I am disinclined to do, I know I'm going to get an x out of the first term, I'm going to get an x out of the second term, and I'm going to get an x out of the third term. So I'm going to have some term, when I multiply this out, which I'm not going to, I'm guaranteed to have a term that has x to the third to it. That means the degree of my polynomial is 3. Based on the degree of my polynomial and the leading coefficient, I can determine what the end behavior is. So if you see this notation an, then that's saying what is the leading coefficient. Well, the leading coefficient in this case, because I get a 1 from the first one, I get a 1 from the second one, and I get a 1 from the third one, my leading coefficient is 1x to the third. My leading coefficient, or a sub n in this case, is greater than 0, which means I'm going to combine these two pieces of information to determine what the end behavior is. So this is a cubic with a leading coefficient that is positive. That means in this quadrant I start down, and in this quadrant I end up in the up position. Now that is not describing the end behavior. That is just a graph for me to describe the end behavior. The end behavior is, as x goes to negative infinity, my function, based on my little picture, goes also to negative infinity. So this is how we describe end behavior, not the picture. The picture will help me actually graph this thing. So as x goes to positive infinity, my function goes to positive infinity. And so those of you who are my calc students in here, you know that is limits. So we accept this as truth in Pre-Calc 1. We prove it as truth in Pre-Calc 2, or in Calculus 1.
Can you get a reminder on the test to not do the graph?
Oh yeah, I will actually give you as x approaches, and I'll leave you a blank, as f of x approaches, and I'll give you a blank, and you just have to fill that in. So with that information, we know that where we're going to end and where we're going to start as I read from left to right. The other thing I have to worry about is the multiplicity of my zeros. So the multiplicity of my zeros, and we're now in 3.1 in Pre-Calc 1, is based on the degree of each one of the individual pieces or the factors. So if I don't see a number there, I can always put a number there, and those are all multiplicities of 1. That means individually those are going to act like lines as I get to the x-axis, which means I'm going to cross through those things like a line, give or take. So with that information, these give me my zeros. My zeros are x is equal to 1, negative 2, and 3. Those are my zeros. They are not my x-intercepts, because intercepts must be wrote as ordered pairs. So as ordered pairs, it is 1, 0, negative 2, 0, and 3, 0. These are my x-intercepts. So zeros are just a list of values that in which we are crossing the x-axis, but they are not actually intercepts. Intercepts must be ordered pairs. Because these all have multiplicity of 1, you'll see this m equals 1, m equals 1, m equals 1. That's the multiplicity. So we're talking about multiplicity. What that means is that each one of these, when I approach these intercepts on my x-axis, I will pass through them like lines. So this is what I now know. I know that I have here -2, 1, and 3. I'm going to start down here. I'm going to end up here. I'm going to pass through each one of these, and I'm going to start bringing this all together. So I'm going to start here. I'm going to pass through there. I need to come back down to this other 0, pass through it, come back to the next 0, and pass through it. That's what the graph looks like. Now, if I want to know exact values, then I wait until I get to Calculus 1, in which I can actually find you where the turning points are on this lovely thing. However, I can always find the y-intercept. The y-intercept I can do without any work. To find the y-intercept, I go back to my original function and I plug in 0. So f of 0 is going to give me the y-intercept, whether it is in factored form or if it's not in factored form. So this is going to be -1 because 0 minus 1 is -1, 2, and then -3. So my y-intercept, the y part of the y-intercept will be 6. My y-intercept is 0, 6. So I come down here and I know that the point that it's going to cross through is 0, 6. Now the whole reason I did this is because I'm trying to determine where this thing is greater than 0. So I'm looking for the x values in which I'm greater than or equal to 0. So I'm looking for where my graph is above the x-axis. I'm above the x-axis in this region, and I'm above the x-axis in this region. So my solution for, which is what I did in the first place, f of x is greater than or equal to 0, is from -2 to 1, and these are both inclusive because I have greater than or equal to, union between 3 and infinity. Now, if I want to do the sign chart, I can still do the sign chart. So let's do the sign chart, and then we have caught you all up to Chapter 3. This is Pre-Calc 1. I have caught you all up to Chapter 3 in Pre-Calc 1. So with my sign chart, what I do is I write my factors on the left-hand side, so x plus 2, x minus 1, and x minus 3. And the sign chart needs to be broke up with, from left to right, your zeros in order. So the first region is when x is equal to -2, and that comes from the factor x plus 2. The next one you're going to have is x is equal to 1, and that comes from x minus 1. And then the last one that you have is x is equal to 3, which is x minus 3. Now let's talk about each interval we have. On the first interval, this is the interval from -infinity to -2, non-inclusive, because I'm not going to include the point in which I'm crossing or touching the x-axis, because I'm not going to actually choose that number, because it's all it's going to give me is 0, which doesn't help me. So then this next region is between -2 and 1, and then from 1 to 3, and then my last region is the interval from 3 to infinity. I do this so that when I go to actually answer the inequality part, I can look at my intervals without any work whatsoever. So I choose a number that is in the interval between -infinity and -2. I'm going to choose x equals, because I'm going to just ball out of control, I'm going to use x equals 100. Because I'm allowed to ball out of control because it's math and let's just do it. So I put in -100, and when I put in a -100 here, I don't care what the answer is. I care what the sign of the answer is. So I put in a -100 in this first factor. I get negative, and the next one is negative, the last one is negative. That tells me this region is negative because I have an odd number of negatives, so that I am negative, which means I am below the x-axis. That confirms what I see here on my graph. My next region is I'm going to choose something in -2 to 1, so I'm going to choose x equals 0 because that is the easiest one to choose. When I put 0 into each one of these factors, my first one is going to be negative and then positive and then negative. This is a positive region, which means I am above the x-axis. And you can see this is where on my graph I am truly above the x-axis. What the sign chart does for us is it allows us to confirm our graph, or it helps you graph. So if you're like, I know how to graph, this will confirm that you have the correct graph. Now I'm going to choose something between 1 and 3, so I'm going to choose, say, 2, because I'm just wild that way. I'm going to put 2 in there, and I'm going to get positive, I'm going to get positive, I'm going to get negative. That tells me I am below the x-axis because of an odd number of negatives, and this confirms my graph that I am below the x-axis. Lastly, I'm going to choose something in that last interval between 3 and infinity, so let's go ahead and just choose x is equal to 100 because it's a nice number. So I'm going to get positive, positive, positive. My region is positive. That means I am above the x-axis, and that confirms that part of the graph. What?
It's the.
So in this, it's actually a quadratic in disguise. The first thing I'm going to do is factor out my greatest common factor. So I have an x to the fourth that's common everywhere, so I'm going to pull that out first. So when I pull out x to the fourth, then I have x squared plus 6x minus 16. So it really is a quadratic in there, and that's where I want to go, because quadratic is a land in which we're pretty comfortable with. So factors of 16 that have a difference, and I know it's a difference because this is negative. So the factors of 16 that have a difference of 6, 8 and negative 2. So this is going to factor into x to the fourth, x plus 8 because it is a positive 6, and then x minus 2. So my zeros, no, I'm not going to give them to you in order yet. My zeros from the first one here gives me 0. This one gives me negative 8, and this one gives me 2. Now I need to put these in order because that's the way WebWork is going to ask for it, is in order. So it'll be negative 8, then 0, then 2. What is the multiplicity on negative 8? 1. So my multiplicity on negative 8 is 1. What is my multiplicity on 0?
4.
So my multiplicity there is 4. And then what is the multiplicity on 2? 1.
Yeah, it was just solely that, like, changing it. I just tried without even factoring it first, and that didn't work at all. So.
Factoring is your friend.
Factoring is your friend you sneak out of the house with your synthetic division this weekend. So you're going to make eye contact with synthetic division and factoring, and you're going to sneak out of the house with them. That long division of polynomials, you're just going to glance at them and look away. And you're not going to tell them your plans at all.
98, 99 last quarter, like both, like one after the other. I forgot to get everything.
That's all cool. That's all cool. I'm just saying you do have the math mind to consider going to calculus. I'm just saying you might want to consider it. Calculus is beautiful. See, it is beautiful. If I were to graph this, I know that I started out with x to the 6th and my leading coefficient is positive. So the fact that my degree is 6 and my leading coefficient is positive, quick little sketch of the graph is up, up. And so as x goes to positive infinity, my function goes up to positive infinity. So my calc students are like, yeah, we know that. We did the limits. We proved that. As x goes to negative infinity, my function also goes up to positive infinity. So I know those information. Now, when I go to graph this, I know I'm going to end up here and I'm going to end up here. My zeros, in this case, because they're all real numbers, will become my x-intercept. So I have an x-intercept at 0, I have an x-intercept at negative 8, and I have an x-intercept at 2. Now, when I go to look at what's going to happen at those x-intercepts, is I look at the parent graph of each factor. The parent graph of the factors of x plus 8 and x minus 2, they have multiplicity of 1, so they're going to act like lines because their parent function is a line. So I know at 8 and negative 8 and 2, I'm going to pass and it's going to kind of look like a line. So if I zoomed in, it's going to look like a line. The parent function on x to the 4th is x to the 4th, so it's going to have a quadratic type shape, which means it's going to touch and bounce back off in whatever direction I come in from. So knowing that that's going to happen, then this is what the graph is going to look like. It's going to come down. It's going to come back up to that 0 because it's going to act like a quadratic there. It's going to touch and bounce, and then it's going to go back up. And that's what the graph is going to look like. Much better drawn than what I have, but that's the basics of the graph. Yes?
You briefly touched on the definition of calculus, the precise definition. Have we ever covered that quite yet?
No, we
That's
won't.
Before integration.
Yeah, it's right before the precise definition of calculus will come right before integration.
There's 3, right?
3 what?
There's 3 like parts of it, right?
Off the top of my head, I believe so. I'd have to look at it. The one that I know, the reason I know that this one, oh, something's happened with eBay. No, I don't care. So the reason I know the fundamental theorem of algebra is because we just discussed this in Pre-Calc 1, which is I am guaranteed to have the same number of zeros as I have as the degree, and those zeros are going to be complex numbers. So these are all complex numbers, negative 8, 0, and 2. They're all complex numbers. If I just do this, I put plus 0i attached to every single one of them.
One of them is that if you can differentiate, you can integrate. But if you can integrate, doesn't necessarily mean you can differentiate, right? Something like that.
I'll have to look when we get there. I don't remember off the top of my head. So if you ask me after we've done it, I'll be able to tell you exactly what it is. The fundamental theorem of algebra, I'm like, I don't know. We did that a while ago. Remember, I can only hold so much in, and then it just kind of goes. Okay, so let's go. So if you're given this graph, what you want to do is first you look at the intercepts, which give you the zeros, which give you the factors. So this intercept is at 2, 0, so the 0 is 2, and the 0 here is 1, or excuse me, 4, because that's 4. So my factor would have been x minus 2, and this factor would have gave me x minus 4. Because this is bouncing, I know the minimum multiplicity has to be even, and so I'm going to use 2. I could use 4, I could use 6, I could use 12, but I'm going to use 2 because it's the minimum one I want, okay? And then because I'm crossing, that has a multiplicity of 1 because I'm crossing right here. I could have used any odd one to work, so I could have used 3 or 5 or 7, but I want to use the minimum one. And then I don't know what my leading coefficient is, so I use a as a placeholder. And I set this as f of x is equal to that. And then what I do is I use that ordered pair right here, which is 0, negative 4, like I did before. And so this is going to be f of 0 is negative 4, a 0 minus 2 squared, 0 minus 4. So negative 4 is equal to, this gives me 4, so a multiplied by 4 multiplied by negative 4. So 1 is equal to 4a. A is 1/4. So I just come back up here to my original function that I had a as a placeholder, and I just replace that a with the 1/4, yeah.
All right, I did everything right except for the multiplicity thing. That's what I missed.
Okay. So, yeah, and that's because it's bouncing, and I had to actually zoom in on that to see what was going on. Because it almost looks like it's sliding through like a cubic, but it's actually a bounce. It's just not a very big bounce, that's why I exaggerated it here on this graph. What else?
That was the last one.
Oh, nice.
Finish the homework.
Nice! So you're all caught up with everything from chapter 1 up to here, or just focusing
No,
on 3?
I'm just focusing on 3 right now.
Okay, that's cool. Just when you have time.
The reason I didn't do good at
Oh,
first
let me
test